here we are again, and I'm here to just give you a little bit of theory associated with the Arrhenius plot and Arrhenius theory that you're going to be using in lab, having to do with the hydrogen peroxide decay process. So a lot of this is in your text in section 15.4. There's Arrhenius, and I'll just get into it. It's not very much. We're accustomed to doing something like this. We're going to say that the rate, this is the rate law for the hydrogen peroxide decomposition reaction, K times concentrations and raised to various orders. It's that very same K that we write according to the Arrhenius equation. This is the Arrhenius equation, okay? And it says that the rate constant itself is temperature dependent. Here's what it depends on. This quantity here is called the frequency factor, big A, and then the energy of activation, that's one thing that we've talked about in class. Here was a reaction progress diagram, and you know that that distance right there is E sub A. So, okay, and this was just, I don't know that it's a two-step reaction, but if it were, that would be E sub A. Maybe we'll talk later about in class about what the meaning of a big A is. Just qualitatively, it's something like this. I've got two things that are going to react, perhaps, but maybe they don't all react. Maybe they have certain orientational requirements for them to react, and that's kind of in that constant A. I take the logarithm of both sides of the Arrhenius equation. That gives me natural log of K, and using the rules of logs, if the log of two things multiplied together is the sum of them, so log of A plus log of all that. And then I do a little bit more logarithmic work here. I know that log of e to the something is just that something because they are inverse functions of each other. So that leaves us with natural log of K equals log of A plus E sub A over R. That came down from the log and times 1 over the temperature. And the whole idea here is that if I had a bunch of measurements of the rate constant for different temperatures, then I could imagine making a graph of natural log of K on the y-axis, and I would put 1 over the temperature in Kelvin on the x-axis. Then it kind of looks like an equation that goes y is equal to some constant b plus mx, okay, where b is natural log of A, and the slope is minus the energy of activation over R. Okay, so this is an Arrhenius plot that I'm about to put up here, and I can tell that the slope should be a negative number, and so now it bears thinking about this. If I have a low temperature measurement, that means temperature is small, okay, that means 1 over the temperature is big. So on this axis, I've got cold going this direction, hotter going that direction. So I make a measurement of the rate constant, and I plot log of K, and then I raise the temperature, let's say, and then I get a bigger number, okay, and then I might get a bigger number, and so on. And, if they lie more or less on a straight line, then what can we say about that? Well, the slope ought to be equal to minus E sub A over R. Okay, the slope is M, which is minus E sub A over R. So if you measure the slope, then you can figure out what the energy of activation is. And what else? We could also get A because the intercept is B, okay, and so we could also get the frequency factor out of it. So that's our theory.